My name is Tobey. I'm an evangelist for Apache Cassandra at DataStax. And what that means is I do a lot of stuff like this, talking to crowds. I travel around, talk to a lot of customers. And the biggest thing that we've been seeing a lot of is the big debate we run into when we talk to a lot of people is, do I buy hard drives or do I buy SSDs? And it's still a debate, and this has been, for those of us that run Cassandra and have seen a lot of different customers, it's always really mystifying when we have this debate, because when you go to a customer who go to a site that has SSDs installed, they usually don't have any problems with disk until they've been in production for months usually. And then it's usually because they're pushing things really hard. So I'm going to just tell you what I want you to walk out of here with is an SSD is going to cost more than a hard drive on a gig for gig basis, right? You can go to Fry's, you can buy a 6 terabyte hard drive, it's something like 4 cents a gigabyte. You can buy an SSD, consumer grade SSD, it's 75 cents, 80 cents a gigabyte. That's a big difference. When you go to finance, they're going to freak out and say, why do you need this? I'm going to show you why you need it. But the big reason why is none of us are probably getting, well, I'm getting paid to mess around with weird stuff, but most of us are not getting paid to dink around with hard drives. We're getting paid to build products, to build facilities for our businesses that make the business move forward. And if you spend that time dinking around with hard drives, that's less time that you could be spending improving other parts of your infrastructure, improving other parts, tuning other parts of Cassandra. You're wasting time with these hard drives, and I'll show you how they're wasting your time. So, disclaimer number one, I'm not a statistician. I'm learning this stuff as I go. I've learned a ton of stats in the last few months. I've been working on this project. There will be some things I might get a little wrong. You're welcome to catch me right afterwards if I say something really incredibly stupid about statistics. Just let me know afterwards. I'd love to know, but please let me keep moving, because I think the numbers will speak for themselves even if I get it wrong. This is not strictly scientific. It is fairly scientific in that I made it as repeatable as it can be. All of the code is on GitHub. All of the data is going to be available in some way. It's pretty big, so I can't just like slap it on a web server and let it rip. It's like 500 megabyte download. So the other thing is I don't have a lot of drive diversity. I tested one Samsung 840, and it's broken. I'll show you. It's really kind of cool. I have one 15K SAS drive. That's not a very good population sample. So that's a problem in it. And then time limitations. I couldn't run a benchmark for 24 hours because I have one machine to run these on, because I wanted to keep the machine the same across all the benchmarks so that they're consistent across, it's not like I get a faster processor so I get better latency numbers. It's the same box running all these benchmarks. So time limitations, all the tests were run for exactly 10 minutes per drive. But I ran, you'll see how many benchmarks, a lot of benchmarks per drive. So that's just one variable that's in there that I want you to keep in mind as we look at the numbers. It could be I got a really crappy 15K drive, but it seems to be fairly normal from my experience. And this is just for the next thing. These are, the sample thing is kind of important. I'm going to pick up really hard on a couple of these drives, and it could be that I'm wrong about this, especially if I have, some friends from Samsung here. The 840 that you're going to see the numbers are terrible because I abused that drive for about 6 months, and it is completely busted, and it's actually kind of cool. But so I don't want you to walk out here with an impression that the Samsung 840 is a terrible drive. It is actually great. I have 3 of them at home. It is my favorite drive that's come out recently. So just keep that in mind. Like, I've been pushing these pretty hard. We generally know why. Moving forward. So here's a little bit of a, all right, I changed the order here. So, benchmarking and tuning, I consider it the art of discovering and choosing trade-offs. So that's what we're talking about. When you buy a hard drive versus an SSD, you have a trade-off of money versus time. You can spend a whole lot of money on SSDs, and you don't have to spend a lot of time, like I said earlier. Or you can save a lot of money, buy hard drives, and you're going to spend a lot of time making them work well. And the same thing goes for, you can trade off latency for throughput, throughput for latency, safety for speed, all these different trade-offs, and this is really what we're after. And what I'm really after is, when we're doing micro benchmarks like what I'm going to show you, it's about what I want to know is what can the drive do? It's not what I'm going to do in production. Running a system at 100% in production is just silly because you're going to be running at the edge of what the hardware can do, and you're going to have more failures, you're going to have more surprises. So while a lot of these benchmarks are designed to torture the drives as hard as I could, what we're finding out from this is what happens when the lights are out, when it's 4 o'clock in the morning and you get a load spike. I want to know that, right? Drive operating under normal conditions doesn't tell us what it's capable of. That's just normal. Like when you go and I'm a runner, right? If I'm going for a run, if I sprint, I can only sprint for maybe a quarter mile, maybe a half a mile. But if I do a nice normal pace, I can run for 6, 7 miles, no problem. And that's kind of another part of one of those trade-offs, right, is to keep in mind is that's what I'm after with micro benchmarks. It's the same thing when you look at things like algorithm benchmarks or compiler benchmarks, processor benchmarks. It's telling you what the hardware can do, what can the software do. It's not telling you what you're going to get out of it. So a little bit on tuning, just to set the level. We're going to get to graphs really fast. So these are the settings that I ran on all these benchmarks on all kinds of drives. Generally, if you have an SSD, these are the settings you want. This is what I've discovered. And I've learned this through a few different people and put this together. But these are the main things you want to do first thing when you have SSDs in a system. So you have this echo1 sudo t no merges. What that does, it tells the Linux kernel to not bother trying to take a whole bunch of IOs and group them, which on a hard drive is a good idea generally because the head, you have those platters spinning and it's like a record player, right? If the head is in position and you push all the IOs down to the drive and it can patch them together, it can write them out in a nice linear write. On an SSD, that doesn't matter even a little tiny bit because they're just key value stores basically in the back end. The other one is read ahead. I'm actually starting to become of the opinion that this is always what you should do, even on spinning disks. Because the thing about read ahead is it keeps your, if you don't need the data that you read ahead, you've just wasted ability to do other I/O on the drive. So the drive is busy reading a bunch of crap you're never going to use. You've just wasted latency. You've just wasted hardware capability. And Cassandra is actually fairly precise in issuing its reads. So even when you do a range scan, Cassandra is going to go down and issue to the operating system a big linear read off the SS table. So it doesn't actually need to do speculative read ahead. So for Cassandra, a lot of time, read ahead's not going to help you a lot. If somebody actually runs into a case where this is wrong, definitely email me or tweet at me and tell me I'm an idiot. And I'd love to know to hear about that. But I'm pretty sure that this is going to be something you can try and get some additional performance. Finally, if you're running a database, I don't care which database it is, anything that cares about latency and you're dealing with hard drives or file system performance. These two schedulers in the Linux kernel, I/O schedulers, no-op and deadline, are the only two that you want to be dealing with. If you're in EC2 or any virtualized environment, no-op is almost always the right choice. If you have a hardware RAID card, you want no-op because the RAID cards typically have their own I/O schedulers built into them. The only reason why you wouldn't do this, if you're running Docker or containers or anything that uses C groups for I/O management, you want to stick with CFQ because it's the only one that supports actually doing that. But otherwise, no-op or deadline. So the difference is no-op says when the kernel receives these I/O requests, it's not going to try to schedule them. It just passes them straight through to the underlying storage as is. Saves a little bit of CPU time. It's hard to measure the difference usually between no-op and deadline. CFQ is actually kind of an atrocity compared to these two. It uses a whole lot more CPU because it's trying to be smart and typically failing. But it's really designed for like desktop workloads or interactive workloads. And we're running databases. There's only one user on the system if you're doing it right. So deadline is a really good safe choice. If you're not comfortable with no-op, go to deadline. If you're virtualized, go with no-op. Hardware RAID, go with no-op. So that's what I ran all these benchmarks with is no-op. So here's just a really quick, I put this on Twitter a little while ago, so some of you may have seen it before, but this is just a quick test I did when I was testing out the Intel 730 drive. And you won't be able to read this, so I'll talk you through it. That's actually why I made the fonts unreadable, is so that you had to listen to me. is, so I start the test here, and I'm looking at dstat, and this is dstat. If there's no other Linux performance tool, if you saw me last year, I'll always keep talking about dstat. This is how I read the matrix, performance-wise. I have this running all the time. I have screen session open on the cluster. I'll be logged into every system in my cluster, and I'll leave this running in different screen sessions. So when you have a performance issue or you think something's interesting, you can actually pop to that screen and you can see the last few minutes of history. You can step back and you can scroll back a little bit and see what happened in the past. And this is really handy, and you should be looking at this stuff all the time so that you have a sense of how your system is performing and what looks normal and what looks abnormal. So what we have is, on this one, I had this running and I took a look, and here's the test beginning, and I see right over here that this is the I/O wait numbers. And this is idle CPU, system CPU, and user CPU. And this is all I'm looking at the moment. And this is running a full-out destroy the drive kind of benchmark at the moment. And what I noticed is I'm using a lot of system time, or a lot of I/O wait time. And an SSD should never have I/O wait time, almost never. These loads are kind of the worst case. And that's really high. So I started looking at some of the settings, and oh yeah, I forgot to turn read ahead off. So I look, and there's 15, 14, 18. I set read ahead to 0. Within 1 second, it drops by 10%. So this is what read ahead does. It not only costs you in terms of keeping the drive busy doing basically BS work that you're never going to use if you're running Cassandra, it also costs a lot of CPU time because the kernel is trying to compute these ranges that it needs to go read from the drive to optimize your I/O. So setting read ahead to 0 drops a whole bunch of CPU time, gives it back to the application. I set it back to 128, which is the default on most Linux boxes. If you're on Ubuntu, it's even worse. I think they set it to like 256, and that's blocks, so multiply by 512. I think it's sectors. And then I drop it back down, and then CPU time goes right back down. So that's something to investigate. You can actually play with this hot on a live system. It's totally safe. I've done this hundreds and hundreds and hundreds of times and never had an issue in the last few years. So that's one. And this is a little bit of a story. I actually had this conversation. And so what happened was, what we're going to talk about next is outliers. And this is one of the things about hard drives that I discovered by accident during this investigation, was they will actually occasionally just disappear for a few seconds. And what it is has anybody heard of a Heisenbug? This is part of where Heisenbugs come from. So you have a hard drive with your data on it, and Cassandra says, hey, Linux, go get me megabyte 1 through megabyte 5 from this file. And Linux goes, cool, okay, got it. And it goes and it issues that I/O to the hard drives. And maybe if you have a RAID 0 behind it, one of those drives will go and it'll go get the data just fine. The next one will go get it just fine. And the next one will go off and just disappear for a little while. It's like your smoker friends. You know, you say, hey, you're going to be over there. And they go outside and they have a smoke and they show up like 5 minutes late always. That's kind of what hard drives are like. SSDs, I'll show you, they don't have outliers the way that hard drives do. Some of them do, like when they get broken, but so an outlier is a data point on a graph or in a set of results that's very much bigger or smaller than the next nearest data point. That's all it is. What does that look like? So these are the first set of graphs that I generated, and this is one of the worst drives I have. It's a 10K RPM SATA drive, 2.5 inch. I've had this drive actually for a long time with my personal collection. Anybody else have a really large personal collection of hard drives? Yeah. I think I still have every drive I've bought for the last like 7 or 8 years. So it actually worked out really well finally. Like, I get to tell my wife, like, yeah, see, this is why I still have all this hardware laying around in the garage. I'm using it for work now. Like, I'm paying the bills with it, honey. So if you look here, there's an outlier. That's what they look like, right? So we have a nice tight band down here at 10 milliseconds. That actually really sucks. Most of the I/O is actually down here. You can't see it because this is a scatter plot of a 10-minute run of the FIO benchmark tool. It generates a log file that has every single I/O in it. So the latency measurement from every single I/O issues to Linux. That's a lot of data. I mean, this whole thing, I'll show you later, I don't remember the exact number. Over 100 gigabytes of data I generated in total. And so you try to generate these graphs, and it takes like 3 days for the program to run to actually generate the damn thing, and then you can't read it anyway. And so here's another one. We're up at, was that 12 milliseconds? No, 120 milliseconds. So that's your Heisenberg, right? There, in a 10-minute run, there are 2, right, that you can see. And what's important about that is if you look at most of the industry benchmarks, and this is why I really got excited about this project, you'll never see those because most of the time when you take the data out of the benchmark tool, in order to present it to people and draw graphs and get it in Excel and things like that, you have to do some kind of aggregation on it. You take an average or you take a mean or percentiles, and you're never going to catch these. And most people who see one, they'll take a percentile and like, what's my 99th percentile? And it'll be like 120 milliseconds. They go, that's not right. And you rerun the benchmark and it goes away. I ran these things probably 100 times, and I could find one of these in every single run on the hard drives. And so it's important to remember, these outliers still happen. These are your Heisenbergs. You get that call, like in the little text message thing I showed you, which is your boss saying, hey, man, we got this one request. Customer complained they got this one request that hung for 1 second when our SLA is like 50 milliseconds. Cassandra sucks because that happened. It's not Cassandra's fault. It's the damn hard drive's fault because it disappeared off to have a smoke. Here's a 15K SAS drive. So this is the one that I fight against all the time, right? Everybody wants to buy the 15K SAS drives. They seem cheaper. They're actually the same price as consumer-grade SSDs, but they're worse. 18 milliseconds up here at the top. We got 6 milliseconds down here. So this is on microsecond scale over here. Most of the I/O down here on the writes are down here. The reads are in this band between 6 milliseconds and 12 milliseconds. That's not terrible. That's actually really good for a hard drive. But you still get these up here, you know, up here at 18 milliseconds. And this is actually one of the better graphs I got off this drive. So that's 15K SAS. And here's, if the time and money thing, this is the extreme case. If you want, and SanDisk guys are going to love me for this until later when I show them where Fusion I/O doesn't do well. This is a Fusion I/O drive. Now, if you have money and you have a problem with I/O and you want to just go away and you don't care how much money it is, Fusion I/O is the answer, always. The new Intel, all the PCIe SSDs are starting to catch up. But if you look, the range, the total range of latency on a Fusion I/O card is from 40 microseconds up right here at this bar. So below 40 microseconds, here's 20. So we're at 5 to 20 microseconds for writes, which is insane. It's basically the PCI bus latency. PCI Express bus latency is around 5 microseconds. And then here is most of the reads, and we're below 100 microseconds. So the scale, we've dropped 2 orders of magnitude. That's a PCI Express card. I've got one in the workstation. It's been really cool to test because it's basically the one that breaks all my crap every time I try something new. The Fusion I/O card will do so much I/O that it'll like fill up my hard drives and break and run me out of RAM and all kinds of crazy stuff. So I generated some more of these. I wanted to do some more scatter plots. These were actually generated at the last minute with R. Kind of also doing a tour of all the graphing tools. These were done with in Go with Platinum, which actually works okay. It's just for Go, it's really slow because it's all float 64s all through and it does a lot of data copying. I know I got a couple Go users in the crowd, so I thought I'd mention that. This is actually R. If you're a statistics person, R is where it's at. And this is like 2 lines of code in R to load a CSV file and do one of these. It was kind of crazy. I was surprised when it worked. So we've got down here 20 microseconds, 100 oh, this is the bandwidth graph. So the main thing you want to see here is this is the spread in the density of IOs. So this is actually a kind of a fun one I threw together because I had all of these drives on the SAS controller. So I had a 15K SAS drive, 10K SATA drive, 7.2K, 7200 RPM SAS drive, and a Samsung 840 SSD. I just threw them into a RAID 0 just to see what would happen because I really wanted to show you with that. And here is IOPS. this is latency. So this one is actually the one I wanted to show you, in that this one, you can't see any of the distribution down here because there are outliers up here that you can't see in the back because it's, you know, typical conference projectors. There's one right there. Right over there. It's like right there. These are the things. These are more Heisenbugs, right? And this is probably the 10K SATA drive. It's a RAID 0 set. And I can show you how I know. How many people have used IOstat to look at I/O issues? So IOstat, in my opinion, now that DStat's on most Linux boxes, has one purpose, and it's for when you're looking at a RAID set, you want to fire up IOstat, and what you're looking at is the A weight column. And what you'll see is, I can tell you which drives these are. I don't remember, but here you go. Here's the 7200 RPM drive. Here's the 10K drive. Here's the 10K drive, 15K drive, and here's the SSD. So it's a really silly way to set up a RAID, but if you want to see how IOstat looks across different media types, and what you'll see is actually if you're looking for a bad hard drive in RAID 0, if you're running in Amazon especially, it's typical to do RAID 0 across a bunch of ephemerals or EBS or whatever, and I'll show you why EBS is evil later. What you're looking for is these outliers, right? It's outliers again. So these numbers are actually made up on the fly by the tool. When IOstat's running, it's actually looking at the ranges as it goes. And so these numbers, it doesn't know what a hard drive can do. There's no table that says, you know, this /dev/SDA can do 500 IOPS. So it has to guess using statistical methods. And it uses the dumbest methods possible, usually, these tools do. And what you're looking for, actually, as a human, is to do a little pattern recognition. You're looking for these numbers to jump by an order of magnitude. And very often, if you have like an ephemeral drive in EC2, what that'll show up as is this one right here, that 435. You'll see variance like, you know, 4 milliseconds to 40 milliseconds or whatever. And that's not what those are, but those differences. But when you see it jump by that much, it's almost always a hard drive that's failing. Or it's just more weirdness in EC2, right? It's hard to say what is actually going on in EC2. Maybe you have a noisy neighbor that's on the same platter, you got unlucky. You need to ditch that instance to get a new one. But this is actually a way to replicate it in on bare metal. So this is the test bench. So this is my old workstation that we use for this. It's a Xeon system from 2011. So it's a pretty representative of a lot of servers. It's a single socket, so there's no NUMA madness to deal with. 16 gigs of RAM, which shouldn't matter too much. And then it's set up so that I can plug different drives in and move stuff around. So what we end up with is running FIO is FIO is like the worst benchmarking tool in the world, except it's also the standard now, in that the user experience of FIO is terrible. In minor releases, it's been the bane of my existence. They'll change the format of output files. The command line flags will change in like .1 releases. So that's been really interesting. But what the interesting part is the output that it gives you on JSON is actually just a bunch of random numbers, and they actually don't make a lot of sense on their own because they've dumped all the resolution, and you don't see those outliers that I was showing you earlier. So what I had to do is pull the latency logs out of it. And this is the kind of data that we had to crunch. So I'm not going to be able to show you this kind of scatter plots from before right after this. But that's just a lot of data. This is what a FIO config file looks like. This is all on GitHub, so if you want to run some of these benchmarks on your systems, it's on my GitHub. It's called FIO, EFFIO, which is kind of just an expression of my rage against the tool FIO. It's a terrible name, and it's confusing, and I should probably change it, but that's what it is. And so almost all the files that I ran look the same. And so I wrote this tool in Go to basically run suites of benchmarks. So it takes a list of drives and a list of benchmarks, does a Cartesian set, and then runs all of those for me. So I don't have to run 300 benchmarks by hand. So just quickly going over FIO file in case some of you decide to do benchmarks later, and you certainly should be benchmarking your hardware periodically so that you have a feel for it. You can set, this is the kind of workload you want. So I want a random read workload. You set your block size. That's almost always determined by the device. If you have a hard drive, it's almost always 512 bytes or maybe 4096. Those are the only two options, really. You can set the I/O engine to things like sync for like direct I/O and async I/O, different things. I do direct I/O for all the latency measurements. This basically says I'm doing an I/O, or just a pure latency measurement. So it says don't do any parallel I/O, just do one I/O at a time, measure how long it takes, then do the next one, then do the next one. So it doesn't tell you a lot about bandwidth, but it does tell you a lot about latency. And then there's just a bunch of other housekeeping stuff. But the main thing here is I run all the tests for 10 minutes, whether it goes well or not. So every test goes exactly 10 minutes. And then it doesn't clean up afterwards, because otherwise I'd still be running benchmarks even if I'd started like 3 months ago, because filling up the hard drives with data, with 100 gigs of data, takes about 20, 30 minutes per test. And if you blow it away every test, then you basically spend all your time filling drives up. So that's actually the end of that. Now I'm switching applications. We switch modes pretty easily. So what we did is there was a lot of data to handle, and generating graphs like images is actually really tedious, and then going through them is even more tedious. So threw this application together to show this. Let me go to something more familiar, and then we'll come to that. So just want to show you a few things right off the bat. So I ran some additional tests besides what I ran at home on my workstation, and included an i2x large instance. Amazon i2x larges, the SSDs, are almost as fast as Fusion IO cards. They're within striking distance. So if you look way down here at the bottom, they're down there. I'll show you a closer view of that in a moment. Up here at the top is Google Compute Engine persistent disks. So when you hear DataStax people say, never, ever, 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 ever use network storage, this is why. Now, I'm not picking on Google, because the nice thing about Google PDs is while they can only, the best you're going to see is 20 milliseconds, and the worst you're going to see is 20 milliseconds. It's always 20 milliseconds. Whether you issue 100 IOs in parallel or you issue one IO, it's going to take 20 milliseconds exactly no matter what. So when you have Cassandra running in Google Compute Engine, it runs great, which is why we have the partnership with them where they're showing 1 million IOPS through Cassandra. The reality is you have to tweak Cassandra to do a lot more parallel I/O, because Google can take as much as you can throw at it. It's the exact opposite of some of the Amazon stuff like EBS, which starts to melt down if you do more than one IOP per an hour. The next one down is this is EBS, this blue line here. I'll get my pointer. Don't use EBS behind Cassandra ever. I mean, if you get stuck with it, we'll support you, but we're going to move you off of it. The main thing about EBS is, you're not going to see it in here, is there's a lot of variance. We'll switch to the box plot in just a moment, and you'll see what the variance looks like. And then moving on down, 7,200 RPM SATA here. There's a 700 RPM SATA down here, but all the hard drives are down in the bottom half of this, or in the middle here. And then the SSDs are all down here at the bottom, and they basically look like they're all at 0 latency, which is why we have this switch here. So what I want you to wanted to really drive home for you is, here's hard drives. So look, when you're looking at these graphs, the line isn't actually telling you that much. What you're looking for is, what's the range, right? So if you look down here at the bottom, here's 0 down here at the bottom. Up at the top, we have 22,000 microseconds, 22 milliseconds. That's hard drives. And then I flip over to SSDs, and we drop 2 orders of magnitude. The total range of all the IOs I did on all the SSDs, the worst one, is up there at 230 microseconds for just raw latency on random reads. And I can flip it over, and here's the worst test that I have. So this test is, and over here on the left-hand side, these are all the benchmarks that I ran. So those are all the different configs. And down here at the bottom, these are all the drives, the different devices that I tested. So what you're seeing is, this is the random read-write 50-50. So it does 50% reads, 50% writes, and it issues both And it tries, this is the worst possible load for a spinning drive, because it's doing, you know, for every 1,000 reads and writes, it's doing 500 reads, 500 writes, randomly anywhere on the disk out of 100 gigs of data. And the SSDs, they don't really suffer. I mean, this one at the top, I think that's the PNY Accelerate, which is one of the cheapest SSDs you can buy. I got that at Fry's. It was like $100. And it's doing 240 microseconds under the worst benchmark I could throw at it. Now, let's go look at the hard drives again. I'll come back to the SSDs. And the best hard drive, which one is that? It's not a hard drive. Oh, that's EBS provision IOPS. But that's because this is a latency test, and they're locking the latency down at the network layer, because EBS goes out over Ethernet. That's the thing to always keep in mind. EBS, they might as well put the E means Ethernet, really. It's not what it actually means. But EBS is running over some kind of IP network. And that's where all the variability comes from. That's where all the failures come from. And this is why it's terrible. Moving on up, though, but like we have at the top, here's Google again. That blue line is, this is EBS, plain EBS. So provision IOPS is a better option. This is provision IO. This is regular EBS. Then we have all the other drives in there, and I don't really need to point them out, except, you know, maybe here's the 15K SAS drive, is this pink line right here. Give a nice color of pink. And so that order of magnitude is the thing to remember, right? SSDs, 200 milliseconds, spinning drives, 200 milliseconds, or 20 milliseconds. Milliseconds. What's the other one I want to show you? Here we go. So on writes, random writes, same kind of deal. The nice thing is most of these are telling the same story, no matter what the workload is. We can go where I'm doing a peak bandwidth, same thing. But the neat thing about the Google one is they actually do fairly well. It's that nice straight line. It's the same no matter what you do. And go back to SSDs. And it gets a little more interesting. Is that the broken drive? That's the i2X large, right? Maybe we'll actually do it this way. There we go. Oh, that's the IO switch one, yeah. I've been abusing that drive. So how are we doing for time, Nick? Okay, cool. So that's basically, I built this so that I could do questions. So with that, I can flip through other stuff. I can show you the median and stuff, but it gets boring from here in that these are all going to show the same story. And that's actually really the lesson that I learned from this. All these benchmarks, I can tell you this exact same story going through SSDs and hard drives. They behave the same. They have basically the same kind of distribution and variability as over all the different benchmarks, whether it's 2575 or 100% read or 100% write. You pretty much get the same kind of patterns, the same kind of layout and ordering of all the drives. There are a few times when, like, the Intel 730 might beat the Fusion IO, which is just really weird, but it just happened to be what they optimized. So with that, I'll turn it over to questions. Yeah? So do you measure SSD degradation full? Yes. Do you say 100 cycles of writing after that? Yeah, I have one for you for that, actually. Let me find somewhere the Samsung 840. Actually, no, I have it turned off, don't I? Yep, right here. Whoop. So that's what I was saying before. My Samsung 840 Pro, one of my favorite drives, and early on when I started this test, it was regularly the best out of the bunch, but it's also the one I've abused the hardest. And it's a 128 gig model, so what I'm doing is I'm running 100 gigs of data. When you fill an SSD up, this is important to remember, the performance will actually start to go bad, especially on the older controllers. The newer controllers like the SandForce and the Samsung 850, they tend to stand up to it a lot better, but you're right, as they fill up and you do a lot of read-write cycles and you haven't done a trim in a while, they will start to slow down and sometimes start to show some really weird outliers. One of these actually has it being the worst drive even among the hard drives. Oh, and I wanted to pull this one. This one actually shows it really nicely. RW 5050. That's not right. Find the right one. There we go. I had one on here that was showing it like, oh, I'm on the median. Doesn't matter for that one. Any other questions? I'll find this while I'm going. So for Cassandra, it's not, you can run consumer grade drives with Cassandra because of the way that Cassandra does write to the drives, because we don't have a problem with write amplification because Cassandra does the immutable SS tables, right? When you fill up a mem table, Cassandra writes that out as a big linear write to disk. And even when you do compaction, it's going to read the two SS tables, write a new one, it's a nice big linear write, and then it unlinks the file. So that's actually where trim gets to kick in nicely, and we're actually kind of the ideal case for a lot of the SSDs controllers. There are certain data models that are going to be better. Like if you're using a lot of TTLs, you're going to be churning a lot more data on the drive and doing a lot more compaction. But typically, like we have customers that are in production on Samsung 840s actually, and I haven't heard that we've had any issues with that yet. So it's not a big deal with Cassandra. I wouldn't run MySQL on a consumer drive in production, but I think Cassandra you can do just fine. And the PCIe drives that are coming out, the price is coming down really fast. Those things really, really cook. Yeah.
So you used FIO for all these tests, right?
Correct.
Out of curiosity, did you run Cassandra stress while you were doing this as well, just to get a better set of numbers?
I did on a few of the drives. The problem is it's harder to measure, to get direct measurements of the drives, and what I really wanted to show is kind of this right here is the spread. So this is these are candle charts. The min, this is the max, 75th percentile, 25th percentile, and the median. And this is really, when you're talking about performance in a database, the latency, right? The low-level benchmark, and this is really easy for everybody else to reproduce as well, which is kind of one of my goals. And yeah, that's something that I'm probably going to do after this, is take all these drives and put Cassandra stress on them and see how long it takes to burn them out. So that's maybe a later thing. Yeah.
Any experience or tests with the impact of trim, especially with respect to Cassandra on it?
I have not done that yet. It is built into the system. It just ran out of time to be able to run all the benchmarks. It takes about 4 or 5 days for it to run the full suite. And I've run it like 4 or 5 times to make, because I keep finding bugs and fixing things, and you know how it is. So yeah, that's on the docket to put on our blog or something later on down the road. Yeah.
Have you done any benchmarking against JBoard?
Yes. Let me, actually, I have in a tab. So I blogged about that a little while ago, and this is actually, I had this handy because I thought somebody might ask about it. So if you go tobert.github.io, I wrote this JBOD versus RAID, and the thing that comes out of this is JBOD is the highest performance option that we have available. There are still some issues around compaction if you start to fill disks up, because right now JBOD is kind of round robin. That's being changed in especially Cassandra 3.0. We're going to have a JBOD aware compaction strategy, I think. You know, there's a ticket. Whether it makes it in or not, I can't really promise it. But JBOD will definitely outperform even RAID 0, and the numbers are on my blog. The other thing that I tested with this one was XFS versus ext4, and really you can flip a coin. XFS is a tiny bit faster. Some people like XFS more, some people like ext4 better. I use ext4 for all my benchmarks just because it's the most standard thing out there is, but you can choose either one, actually. And DataStax supports both, so. Anything else? All right. I think that's time, isn't it, Nick? All right, thank you.